Siebert got his PhD in 1992 under Hans Grauert and Mark Gross in 1990 at Berkeley under Robert Hartshorn. And they're going to talk about local mirror symmetry in the tropics.
Okay, thank you. I'll try to handle these things simultaneously. I won't screw up. So first, of course, I'd like to thank the section committee for giving the two of us occasion to present our joint work over many years at this occasion. And the second thing I would like to mention before starting with the proper talk is it's an apology of the title. There was some confusion on our part where to submit this title, and it's the title obviously a preprint that is appeared in the program book. So the proceedings is of course a more narrow thing than in this talk. Okay, so this is a survey on results that we did over the jointly over several years, 13 years I think, old. Okay, so what is it about? We construct a class of certain canonical degenerations of algebraic varieties, so that's a family map pi x to t, and you should think of an example. Let's say a degeneration of quartic surfaces, product zi plus t, some zi to 4 equals 0, in P3 cross some parameter space. Let's say here we take t equals say k double bracket t, k as field. So degeneration technically here meaning the pi is flat, and in our case x is algebraically complete. That means if you don't know this term, you could think of something proper, but it's also important to admit affine examples. So in general, it just means it's proper over an affine scheme. This affine scheme is of course not T in general, but something sitting in between. The parameter space T can be the spectrum of a complete local ring, or domain rather. The central fiber, and that's a very important feature of our construction, is a union of toric varieties. So if you look at this example, if you take t equals 0, you're left with product zi equals 0, and you just get the union of coordinate hyperplanes. In P3, that's a union of toric varieties. So it's a kind of maximal degeneration in the sense that you break some kind of non-linear, non-toric objects, here it would be a K3 surface, into something that just looks extremely simple, a union of toric varieties. And the generic fiber, so P non-zero, or here in this case a generic point, is a variety with effective anti-canonical class. So that includes Calabi-Yau varieties, Fano varieties, affine varieties, etc. Because I'm not sure what the audience really is here. If there are people who are absolutely lost already at this slide or with some of these things, there are too many young faces also, I would like to give the occasion to ask now. So for example, flatness or something. So, I mean, we are giving this talk not for us, but to explain, to transfer something to everybody. Any questions? The pi? Yeah, so, right, so pi is certainly subjective, that is having to do with the flatness. Yeah, think of subjective and think of proper also. Just the usual degeneration, deformation, I say that. Okay. Now it doesn't work, sorry. Now it does. Okay, so let's talk about the main features of the construction. I mean, that just looks as a construction. Why is that interesting at all? So the first thing is it starts from completely discrete. You could say tropical data, if that term means anything to you. If not, just ignore it. So B is a triple, B, P, phi. So B is a real affine manifold. That means it's really a manifold. As you know from differential geometry or topology, it comes with a real affine structure, and it is even integral. So it has coordinate changes not in diffeomorphisms, but in integral affine transformations of Rn. And P is a polyhedral decomposition of B, and of course it's compatible with this integral affine structure. So you should think of B as being glued together from integral polyhedra. And phi, some additional data that we kind of sweep under the carpet in the form, but it's very important data. It's a piecewise linear function. So if you have know about toric geometry, that's a situation turning up in toric geometry quite often. The B could be Rn, for example. The polyhedral decomposition could be a fan, and phi is then giving the data of a line bond line. Ample. And then it works order by order around the closed point. So in particular, the central fiber, so at t equals 0, modeling out t, can be readily read off from this B and P, this polyhedral decomposition, essentially just by thinking of each polytope as the momentum polytope of the toric variety, and then you patch together just as the picture suggests. And the phi that provides standard toric models for this deformation. Yeah? So you start with x0, you want to deform, write down some family. Toric geometry makes you a standard suggestion, and that is captured by the phi. And then the point is, if we don't want to just do toric geometry, which sometimes also is included in here, but if you want to do something more interesting, is that these phi, the toric models actually don't patch consistently. If you try to patch, it doesn't work. But it works to order 0, of course, because x0 patches. And then you introduce this order by order workings, corrections to these standard toric models, non-toric corrections to the way things are glued together. And these corrections are carried by walls. And it's a very wall structures that are popping up in many branches of algebraic geometry these days. And these are just codimension 1, indeed in this case, one polyhedral subsets of B. Okay, and the correction at next order is determined by an algorithm. There's a certain scattering procedure at the transverse intersection of walls. So walls intersect, they are not equal, they intersect in codimension 2. And the next step, you insert certain new walls emanating from this codimension 2 step. And then the whole process only depends on the choice of initial walls. The initial wall doesn't look like it's data you pick here, but there's some kind of universal choice for these initial walls. So the walls carry some additional data that I will indicate in a minute. And that's the choice of these initial walls is captured by this universal base space T. Okay, that's the moduli space of initial walls. And then the algorithm tells you, okay, you can do into any one. So just to give you an idea what this looks like in practice, the generation of cubic surfaces, the alpha manifold is one indicated, embedded as a subset of R2 with these vertices. The dotted lines, well, there are singularities I haven't mentioned, so the interesting cases are when the alpha manifold has singularities in codimension 2 that you have to remove. And then I cannot draw a global chart, but I have to take cuts, and these are indicated by these dashed lines. So it's a fundamental domain for B minus these lines. And then there's a polyhedral decomposition, looks pretty obvious here. These are the integral points. And then I have to specify the PL function is given uniquely by specifying it to be 0 on this sigma 0 and then taking value 1 here. Piecewise linear function. Okay, and then there's some starting data that takes a form of some polynomial, 1 plus x, 1 plus y, 1 plus z, and x and y and z should be thought of monomials coming from toric geometry that live naturally in this picture. And then you start scattering, or start inserting walls, and you see there's some problem here, you have to insert more walls to make things work. And in this example, just 3 walls suffice. That's a bit untypical. Typically, you expect infinitely many walls. Here 3 suffice, and then you can really read off the degeneration as an explicit equation. Okay, so let's look at the main features of the construction in case you got lost at the first, second slide. Start from these discrete data. The discrete data tell you the central fiber from these momentum polytopes giving the polymer decomposition. And then this phi gives you some standard toric models that, however, don't fit together. You have to correct them, starting from initial walls that are captured, the modular of initial walls are captured in this parameter space T, and then you, by the scattering procedure, you keep going, fit in more walls to make things work in the next one.
So, if I can ask you a question, for example, with the cubic surfaces, what's the claim in the end about the space you get? Is that universal deformation space? Or
it will be a universal deformation space for the singular fiber in the correct language. So it's actually universal deformation space in a logarithmic sense. So there are some non-smoothing directions. These we don't see. We shouldn't see. Boring. And the rest is indeed universal deformation. So this, yeah, we'll get to that. It's useful to compactify modularized spaces. Okay, so what is it good for? We have several slides on this. So our original motivation was mirror symmetry. And mirror symmetry in this picture is very easy to see because there is a perfect duality on these triples, BP phi, to B check, P check, and phi check. I don't want to give this in detail. Essentially, it's B and B check are canonical or homeomorphic. Go over to the barycentric subdivision, and then they are the same. The two barycentric subdivisions are the same. And the P check are the dual cell decompositions in this sense. And then how do we get the maximal cells of the dual cell of this B check? Well, the maximal cell should be dual to a vertex in B. At a vertex, you have this convex PL function. Okay, you look at the representative of this PL function at the vertex, and you can look at the slopes in the dual spaces, vertices in the dual space. Takes a convex hollow of this. So this could be viewed as a Newton polyhedron of this PL function, and that will be the maximal cell in the dual complex. This duality explains most of the known mirror constructions, most notably the largest class of mirror construction given by complete intersections in toric varieties due to Butler and Borisov, or its generalization by giving Tau-Bory-Waffer to somewhat positive cases. We do know some cases where mirror symmetry does not fit into the picture, to this picture on the nose, but there are some modifications you can do, and we believe that in all cases this will be our construction combined, this construction of universe families combined with the discrete Legendre duality is the basic mechanism behind mirror symmetry. So let's do some mirror symmetry for P2, for example. So P2, that looks very similar to this picture B that we had for the quartic. This F and F geometry, this is a different picture. Okay. So you see here outside the momentum polytope of P2, if you have a little experience in toric geometry, but it's split into three kind of weighted P2s. That's a central fiber, so it will give a degeneration of P2 in a union of three weighted P2s. And the general fiber is not just P2 with a union of three lines. I should note that the boundary of your pictures gives a divisor in your family, and it's an anti-canonical divisor of fiber lines, or the total space. So here's an elliptic curve. It's actually a smooth elliptic curve. So this is not torical. Torical P2 would come with three lines, but here you actually get a smooth elliptic curve. And then the mirror transform, this discrete Legendre duality, well, let's just look at this vertex. That gives us sigma 0 with the appropriate choice of phi, this PL function. And then you have these boundary components a dual to rays going out, unbounded cells. And a funny feature in this process, in this picture is that actually, because you have these removed lines here, it looks like you have an edge, but that's actually not true. If you take a chart here, that is a straight line. Yeah, that's a straight line. So the whole boundary is just a circle. It's an affine circle that translates into the fact that this is an elliptic curve. On the mirror dual picture, it translates into the Legendre dual picture, it translates into the fact that these unbounded edges are actually parallel. So it looks more like a prism from a certain perspective. Okay. And the unbounded thing, so much as cases with boundary come with an anti-canonical divisor, the unbounded cases come with a canonical set of global functions that we'll get to, and which here provides a Landau-Ginzburg potential. So mirror symmetries, cases with boundary are mirror dual to stuff, affine stuff, or unbounded stuff with Landau-Ginzburg potential, holomorphic functions. And in a certain chart on sigma 0, that indeed gives the norm given Tanori buffer mirror W equals x plus y plus 1 over n squared. Okay, so what is it good for? Part 2. The original motivation, as mentioned, came from mirror symmetry, but as you see, the construction of these families has nothing to do with mirror symmetry. It just stands by itself, and as such has many interesting properties. So we just construct some class of canonical degenerations, canonical degenerating families of certain algebraic varieties. And why is it interesting? Why do we expect this class of degenerations having so many interesting features? Is that is inherently related to mirror symmetry, and that we expect that any entity arising in mirror symmetry, which is such a multifaceted phenomenon, arising in so many incarnations, can be conveniently and rigorously expressed in terms of A data. And we're far not through with this, with finding out how to express all these things. So examples, things that are partly done, many still conjectural and full generality. Where's the limiting mixed hot structure that comes with such a degeneration? We hope to be able to read off the variation of hot structures, which is not just a linear information as this, but has information to all orders, more explicitly captured by period integrals. We have canonical coordinates, I'll get to that, on the parameter space that comes from mirror symmetry. Or in situations of mirror symmetry, we hope to get, in some cases we do, have Gromov-Witten invariants. Models for the Fukaya category, there's a tropical Morse category that captures, or is supposed to capture the Fukaya category. The mirror dual side that would give a model for the bounded derivative category of Fourier sheaves. We hope to get Donaldson-Thomas invariants one day, and so on. There are many other partly conjectural applications in relations to other works. Well, first you get a construction of interesting families, much as in toric geometry, but with more interesting, or maybe more interesting, more versatile models, not just rational varieties, with full control of their properties. Let's say the topology. All constructions come with a canonical set of functions of a polarizing line bundle that we call generalized Theta functions. Get to that, or Mark will get to that. They can be viewed as a kind of geometric quantization, fits into what people have been doing in geometric quantization. There's a conjecture of Linear application to more classical algebraic geometry on the duality of certain cuff surface singularities. There's relations to cluster varieties that shed light on questions in cluster theory. There are Floer theoretic mirror constructions that should be compatible with ours. Applications to geometric compactifications of moduli spaces, for example, of K3 surface. Again, we will get to that. And then the big question mark on arithmetic applications. Because much as in toric geometry, our construction, when you have, does not only live over fields. If your starting data for walls lives over some ring of characteristic 0, then the whole construction lives over this subring. So quite often you can even construct things over Z. So let's get to some results now. The rest of the talk will give a couple of results along with examples. So let's start with a rather old result from 2008 on Hodge theory. So we have this GP5, the corresponding degeneration. Then we have the complement, the inclusion of the complement of the singular locus, that's B0, large part of B. And then on this part, we have well-defined affine structure, integral affine structure, so there's a local system of integral vector fields. I need this notation because with this lambda, you can produce something like affine Hodge groups. So this is a piece wedge power of this lambda. Maybe you would expect lambda dual, but we have the momentum polytope side, so this is correct. They push forward, make this into a complex Lorentz sheaf, local system on B, and takes a Q's cohomology group. So that's like an HPQ affine Hodge group, and turns out that this is actually the HPQ logarithmically on the central fiber. But this is actually also the stuff that you get the Hodge groups on the general fiber, because we also have a Bayes-Stein's theorem saying that these high direct images are locally free. And to get the mirror symmetry in here, so if you have this discrete Legendre transform with a mirror dual degeneration, then there's a canonical isomorphism between lambda, the dual of lambda on B, and the dual and the lambda on B check. And then on the nose you get this identification. So maybe we could have written equal here. It's a canonical isomorphism that gives the classic exchange of Hodge numbers with this exchange, assuming these are identical. I was mentioning canonical coordinates here. So there are these maximal degenerations that we were producing, and the arising mirror symmetry. They come with a distinguished set of holomorphic coordinates that are given essentially by certain x of quotients of period integrals. So that would be the period integral that is invariant. That is the one that has a log t behavior, and then you take these kind of coordinates, and they're entirely intrinsic, and a result known to essentially proof by me already in 2008, and being written on Woodard at the moment, is that the monomials on this parameter space, so this Q would be some universal choice of initial walls, it's a monoid, these are canonical coordinates in this sense. It's a very important feature of the construction, because this tells you that we can actually, it's not only a formal family, but will be the completion of an actual convergent analytic family. Okay, before I turn over to Mark, let me let's start with discussing a little bit the scattering procedure that is intimately and astonishingly related to Gromov-Witten theory. So the inductive step of our construction inserts new walls at these intersection points. So here, let's say, maybe it should be green. These are the singularities. There's a polymer decomposition. The initial walls just live like close to these singular points. And then you see that at these points where you hit the next vertex, there's a consistency problem, because you've changed this gluing, but you haven't changed the other gluings. To fix this to the next order, you have to continue. You just have to continue straight away, then you change this gluing and everything's fine. But here you get a problem. The change of gluing is non-commutative, and this means you have to glue in two different ways. That would be inconsistent. And at these points you have some scattering process that will produce new walls. And I'm now turning over to Mark, who will explain what the scattering process has to do with Gromov-Witten theory.
Okay, so continuing from here. So there's this process that, as we mentioned on the previous slide, Kunsevich and Sobin had introduced in 2004. And working with Ponderokonde, we gave a Gromov-Witten interpretation for what's going on. So I'll exhibit this more clearly in the next slide, but essentially the situation is that you have some finite number of incoming walls at a given order, and the, let's say, coming in from directions n1 through nr, and these walls always have functions attached to them. And then if you focus on one outgoing wall that you have to add by this scattering algorithm, say coming out in direction m0, the basic statement is that the logarithm of f0, where f0 is the function attached to this outgoing wall, these are given by relative genus zero Gromov-Witten variates on the toric surface, whose fan is given by all of the rays generated by these various anomalies. And so the point really is that this is already a manifestation of mirror symmetry at a very basic, very simple level. Namely, on one side you're modifying the complex structure, and on the other side you're counting holomorphic curves. And we believe that this theorem will lie at the heart of a proof of mirror symmetry. So to give an example, you could, for example, have two incoming directions with function 2 rays that collide with these attached functions, 1 plus x cubed and 1 plus ty cubed. The scattering in this case is very complicated. There's some discrete region with chambers, but mostly there's a region here with rays of every rational slope appearing. And there's some fascinating structure here. But we can look, say, let's look at the line of slope 1, the ray of slope 1 coming out, and try to understand what's attached to that. Well, it turns out it's a very complicated function. We know what function it is. It's some formal power series. I'm indicating it by taking the log. And let me show you, for example, how this coefficient 55 is interpreted here. So this is the fan for P2, so I draw P2. The fact that I have these powers of 3 here tell me I should select 3 points on each of the coordinate axes corresponding to these incoming rays. And then we count, because of this cube here, we're going to count cubic rational curves, which have the property that when they cross one of these two axes, they have to cross it at one of these marked points. So we're not allowed to cross over here. Finally, for the outgoing ray, so the divisor corresponding to the outgoing ray, we would demand that the curve intersects only at one point, but we don't specify which point it is. It just has to be a point of maximal tangency. So the cubic curve that we've drawn here, nodal cubic, is one such curve. And the total counting is given over here. If we fix which points we go through with multiplicities 2 here and 1 or 0 in other places, we'll get 3 choices. This factor of 12 has to do with the fact that you can choose where the double point goes and which point you miss in 12 different ways. That accounts for 12 times 3 curves. The term 18 accounts for nodal curves that go through all 6 points. The node appears somewhere other than one of those 6 points. And this 1 is actually accounting for triple covers of lines. The total is 55 and accounts for the coefficient 55 here. So the basic point is that there really is a enumerative interpretation, very simple enumerative interpretation for this scattering process, and the belief is this will lead to ultimately a solid proof of mirror symmetry from this tropical viewpoint. So moving on, another theorem that's currently almost written up is that our degenerations come with a very natural basis, which we call theta functions. So they always come with a relatively ample line bundle L, and every positive power of L comes with a basis of sections, canonical basis of sections, indexed by points on B. This notation here means points on B whose coordinates are in 1 over D times the integers. So coordinates with denominator at worst D. So there are several features of this. First of all, the description of these really came from third theory, predictions from third theory, which were tropicalized. So conjecturally, these have a symplectic interpretation in terms of counting holomorphic disks. So far, we don't understand in most cases what these are in terms of algebraic geometry. So this is really a formal, family of a speculative formal of a complete local ring, and we don't really understand when they extend past this formal setting. But certainly in some very nice cases, we know much better what they are. So the reason, for example, that we call these theta functions is that if you apply this technology to the case of a billion varieties, this construction gives you precisely classical theta functions. It gives a very nice way of thinking about classical theta functions. In the case of degenerations of toric varieties, the theta functions are just what you would expect, namely monomial sections of line bundle. And just to take another explicit example, in the case of the Dwark family, degenerate family of quintics, you can actually show using representation theory that the level 1, so the D equals 1, the level 1 theta functions are just the coordinates Z0 through Z4. But in general, we don't know whether these sections are algebraic, extend algebraically. A lot of interesting questions there. Here's another result that came out of our program, and this is joint work with myself with Hacking in Kiel. We started with a very general mirror construction for surfaces, for rational surfaces, where you start with a projective rational surface y and a divisor d. It's an anti-canonical divisor, effective divisor, which is a cycle of rational curves. So I'll write d equals d1 plus dot dot plus dn. Now, we can associate to this pair something which we can think of as being kind of generalized fan. So we write B sigma. B is one of these affine manifolds with singularities we've been talking about. And sigma is a polygonal decomposition into cones, but I want to think of it, visualize it as a fan. In this case, B is homeomorphic to R2, and it has an affine structure with singularity at the origin, which I should say is a bit different than the earlier examples we've seen. So describing this very briefly, I draw here a kind of an abstract fan. Each one of these cones in the fan should be viewed as just affine isomorphic to the first quadrant in R2. But to describe the global affine structure, to describe the affine structure across the edges, I need to define a chart in the neighborhood of each ray. So for example, here's one ray, and I will have a one-to-one correspondence between these rays and divisors on the boundary. So this ray might correspond to a divisor di, and I just define there's a unique choice of homeomorphism between this region and the region I've drawn here. This is a fan, this is unbounded, where the fan is given by rays generated by 1, 0, 0, 1, and minus 1 minus di squared. So there's a unique identification of this region with this region, which is integral affine on each of the two cones. And that completely specifies the affine structure. Where does this come from? This is the fan for which the divisor corresponding to this ray has self-intersection di squared. So you can think of this as just pretending that this pair YD was a toric variety and start building the fan using what we know about self-intersections of divisors on surfaces for toric varieties, and then you find out that when you get back to where you started, things don't quite match up and you have to glue, and that gives you the singularity. So, using relative Grove-Witten variants of this pair, and specifically counts of rational curves in Y meeting D at one point, we can construct one of these wall structures which tells us how to construct the mirror to YD. And in particular, we get a affine mirror family, so which we call X, and it's living over a completion of K bracket any of Y. So any of Y is the monoid of effective curves in Y, and we complete along the zero-dimensional stratum. So it's a completion along zero-dimensional stratum of the toric variety. And this construction has several features. So for example, if D supports an ample divisor, say if we're doing Del Pesto surface, the construction suddenly becomes algebraic, and the family extends over the full affine toric variety. And actually, just going back to David's earlier question, if you apply this to the cubic surface, the mirror gives you the universal family of cubic surfaces, modulo some extra parameters which you can divide out by. In another extreme case, if D is contractible, in which case it's contracted to what's known as a cusp singularity, the mirror family contains a smoothing of the dual cusp singularity, which was a notion introduced in singularity theory in the 70s. And this actually proved a 1981 conjecture of Lohenga characterizing smoothable cusp singularities. So this was kind of an unexpected application for us that sort of shows that mirror symmetry does have applications outside of its original sort of domain of interest. So let me just say the difference between what this work and the original construction of myself and Bernd is that we allowed singularities at a vertex. And in this case, there's no sort of a priori defined initial walls, and we need to use some other input, in this case, the Grove-Witten theory of the thing we're starting with to construct the family, to construct the wall structure. And this wall structure comes pretty much by reversing the work we do with Andre Blondet. Okay, so let me give a few examples. So here's the type of example of such an affine surface. Start with the fan defining del Paso surface of degree 6. So this is just R2, no affine, no singularity here, it's just ordinary R2. And this is the fan defining that del Paso surface. And divide out by negation. So a fundamental domain for negation, for example, would be the upper half plane. So you can try to picture the quotient by taking the upper half plane and identifying the positive and negative x-axes. This has some curious features. If you're not used to thinking about affine geometry, a straight line here comes in and out in parallel directions. So there's several things you can do with this particular example. So you could go through our construction without any wall structure. And it turns out it works in this case. If you have no corrections, no wall structure to modify the gluing, you actually get a degeneration of what's known as the affine Cayley cubic, which can be described as just taking the algebraic torus and divide out by essentially negation in the torus, right? Inverting the coordinates. And the equation of the family we get is this. This is for any t not equal to 0, this is a famous cubic written down by Cayley, which has 4 ordinary double points. But you can actually decorate this. So there's a consistent wall structure which comes from counting rational curves on a cubic surface. This affine manifold is the one that arises from the cubic surface with a triangle of lines on it, as for D. And it turns out that a ray of every slope appears as a very complicated wall crossing structure. And then when you produce this mirror family using that wall structure, you actually get this family of smooth cubics in general. Of course, there will be some special points corresponding to these more degenerate cubics. Okay, so another piece of work which we alluded to earlier is ongoing work with Paul Hacking and Sean Keel, trying to apply some of these ideas to compactifications of moduli of K3 surfaces. So for example, you could start with the moduli stack of K3 surfaces polarized by some line bundles at degree 2g minus 2, call this moduli space Fg. And it's a basic problem to try to understand whether there's a natural compactification of this moduli space, which is geometric in the sense that you have a family of degenerate K3 surfaces over which, well, you have a family of K3 surfaces which degenerates over the boundary. There are many compactifications of Fg, but they're not geometric. Now, there's some old ideas of Morrison, David Morrison from the 90s, that suggest that you can actually use mirror symmetry to try to construct compactifications of moduli spaces of Glaviau's. And the idea, very roughly, is that if you think of taking the mirror family to, say, a K3 surface of polarizing this degree, the mirror family is a one-dimensional family of lattice polarized K3 surfaces. And you can take a look at the Morey fan of that family, the relative Morey fan of that family, and use that to construct a toroidal compactification of Fg bar, of Fg. So we seem to be fairly close to carrying this out. I'm a bit reluctant to make precise statements at this point. But basically, we can do something very similar to what we did for this rational surface case. We can use this family and use Gromov-Witten family, Gromov-Witten theory, essentially on the central fiber, to construct a mirror family, again using our wall crossing structure technology. And this allows us to, at least locally, produce some compactifications of Fg near the zero-dimensional stratum corresponding to the maximal cones of the Morey fan of Y. And then there's a question of how much can you extend these families, which are very defined formally over these completions of these zero-dimensional strata. We try to extend these families over much bigger strata in the hopes that this will provide a compactification. So I think we're pretty close to providing something useful there. So let me just end with some cute examples. There are lots of examples of affine manifolds which you probably are well aware of, but aren't aware you're well aware of them. You could take an icosahedron. So each of these faces you should think of as being a standard simplex. Right? It has the affine structure of a standard simplex. You can then flatten out the icosahedron along the edges. Imagine, for example, the usual way that you try to make a icosahedron out of paper. You first draw it in a plane, and then you have to start folding. Now, of course, something goes wrong with the vertices. You can't extend the affine structure across the vertices, and that's where the singularities are. So you actually have 12 singular points. And so it turns out that this affine structure comes naturally from looking at an old construction that Jan Stevens had, where he constructed a degeneration on K3 surfaces to a dodecahedron whose faces are made on Del Paso surfaces of degree 5. So you take 12 Del Paso surfaces of degree 5 and you glue them together to form a dodecahedron, and he proved that these things can be smooth. So you have this family, and if you use that family to construct a mirror, you will find you have to start with this affine manifold. Now we suspect that the structure, the wall crossing structure we need here is very complicated, so, but we don't know. Okay, so as a final example, this makes contact with our proceedings talk, our conference proceedings. This is a three-dimensional example, and this actually really starts to show some of the interest in higher dimensions. So this is an example, or an attempt to draw an example corresponding to local P2s. That's the total space of the canonical bundle of P2. It's a Calabi-Yau threefold, non-compact. So the way you get this is you start with this two-dimensional polygon, you subdivide in the way indicated, and then you attach two pyramids above and below. But you have to define the affine structure in a slightly tricky way. You have to define charts, sort of in neighborhoods of the four vertices of this planar region. And it will produce a one-dimensional discriminant locus, which looks like the dotted red lines. So it's not too hard to define, but it's a bit hard to draw. And when we apply our construction to this, we get a compactification of the almost the standard mirror of local P2. So if you look at the early papers on local mirror symmetry, the mirror to local P2 is the following. It's given by UV is equal to this Laurent polynomial. This lives on sort of affine space with coordinates UV across the algebraic torus with coordinates x and y, and T is our deformation parameter. So this gives a mirror family to local P2. But if we apply our construction, this construction actually gets modified. Essentially, the wall functions are changed in a very slight way. It has to be modified in order to get the obstructions to vanish. There's a specific way you have to modify these functions. And in this case, you get a certain power series, which starts with minus 2t plus 5t squared and so on. And the miraculous thing is that once you make this modification with this power series in t, t is now the canonical coordinate in the sense of mirror symmetry. So this exhibits the fact that we do get canonical coordinates. And you already can see it. So the first interesting case is really this one. So I think that is it. So thank you.
Thanks. Questions? Comments?
I have a question, if it's not too realistic. You said that your construction will cover most of the known occurrences of mirror symmetry.
Right, that's our hope, yes.
Yes, but mirror symmetry means the known cases, or mirror symmetry means possible future cases, maybe not related to telemetry in any way.
Yeah, so, you know, I always like to say that mirror symmetry is like obscenity. You can't define it, but you know it when you see it. So, I mean, it's our belief that any real mirror symmetry construction should fit into at least some generalization of this picture. That there has to be some kind of limiting object, which is tropical, and that tropical object sees the shadows of the two.
So if I have a Calabi-Yau degenerating into normal crossing,
Right.
Abstractly given without any relation to an ambient space,
Right.
then the question is, can you make your machinery work?
So our expectation, so in that generality, it doesn't work yet, but yes, our expectation is that with a bit more technology, we can construct mirrors to normal crossings. Maximally input, normal crossings degenerations. Yeah.
Any other questions? I wanted to ask about the Loyenga example that you mentioned. Perhaps you could state it exactly, and is that among the actually proved things?
That is proved, yes. It's been on the archive for 3 years, so it's still proved. So the statement, Loyenga's statement is that if you can realize, essentially, if you can realize a Cuss singularity inside a rational surface, then the dual Cuss singularity is smoothable.
I see. If and only if, or?
If and only if. So he proved one direction, the easier direction, which doesn't, smoothability implies existence of the rational surface. We prove the presumably harder direction.
Other questions, comments? All right, then in 13 minutes, we'll have Kim talk. Thanks.